3 minutes. That's all it took. 3 minutes of full throttle, boost gauges buried past the red line, Merlin engines screaming at pressures Rolls-Royce said would destroy them. 3 minutes for squadron leader Peter Channer to prove that one mechanic's illegal modifications could turn a wooden bomber into something the Luftwaffe couldn't catch. April 19th, 1943. 2 Focke-Wulf 190Z closing in over the Ruhr Valley. Channer's Mosquito, serial number DZ41144, shouldn't have survived. But it did, because a sergeant named Roderick Banks had decided that Rolls-Royce engineers, sitting safely in Derby, didn't understand what survival really cost at 24,000 feet. This is the story of how bending the rules saved lives. How a fitter, not an engineer, just a fitter, read between the lines of technical manuals and found power that wasn't supposed to exist. How his modifications spread through Mosquito squadrons like a secret handshake, cutting combat losses in half. How Rolls-Royce eventually admitted he was right, and how the man who changed everything died in suburban anonymity, his name absent from the history books. But we're getting ahead of ourselves, because before Banks could break the rules, someone had to build an aircraft worth breaking them for. November 1938. Geoffrey de Havilland walked into the Air Ministry with a proposal that should have gotten him laughed out of the room. He wanted to build a bomber, from wood, with no defensive guns, no armor plating, no turrets, no bomb aimer's compartment, just 2 seats, and a prayer that speed alone would keep the crew alive. The Air Ministry's response was polite, professional, and utterly dismissive. This was 1938. The Hurricane was entering service, the Spitfire following close behind. Metal was the future, aluminum stressed skin construction, retractable undercarriages, enclosed cockpits. Wood belonged to the Great War, to canvas and wire biplanes that had no place in a modern air force preparing for mechanized conflict against Nazi Germany. But de Havilland wasn't proposing nostalgia. He was proposing pragmatism, wrapped in innovation. Britain's rearmament was accelerating, but aluminum was becoming critically scarce. Every fighter, every bomber, every transport aircraft competed for the same limited supply of metal. De Havilland recognized what others saw as an obstacle. His company had spent decades perfecting laminated wood construction, birch plywood bonded with Ecuadorian balsa, and Canadian spruce using casein adhesives, developed originally for furniture manufacturing. These techniques produced structures that were light, strong, and crucially, buildable by skilled tradesmen who had no experience with metal airframes. Piano makers, furniture craftsmen, carpenters locked out of conventional aircraft production could build this bomber. The Mosquito wouldn't steal resources from Spitfire production. It would create capacity where none existed. The design that emerged by late 1939 was audacious bordering on reckless. 2 Rolls-Royce Merlin engines, the same power plants driving Hurricanes and Spitfires, mounted on a streamlined fuselage with a 54-foot wingspan. No gun turrets, no defensive armament at all, just a pilot and navigator crammed into a cockpit, betting everything on mathematics and speed. The performance estimates promised something extraordinary, a top speed exceeding 400 miles per hour at altitude, faster than any fighter then operational. Speed as armor, speed as weapon, speed as the only thing standing between a crew and a very short, very violent end. The first prototype, painted bright yellow for visibility during test flights, lifted off from Hatfield Aerodrome on November 25, 1940. Test pilot Geoffrey de Havilland Jr., son of the designer, advanced the throttles and felt something unexpected: eagerness. By February 1941, official trials at Boscombe Down confirmed the numbers weren't fantasy. At 22,000 feet, the aircraft touched 392 miles per hour. This was a prototype, heavy with test equipment, engines not yet optimized, and it was already outpacing operational fighters. The Air Ministry's skepticism began fracturing. Orders followed. Production Mosquitoes started rolling out of factories, some conventional aircraft plants, others converted furniture workshops, where craftsmen who'd never seen an airplane suddenly found themselves building one of the war's most sophisticated aircraft from laminated wood. By late 1942, Mosquito squadrons were flying deep penetration raids into Germany, hitting targets conventional bombers couldn't touch, photographing installations fighters couldn't protect. The concept worked, but there was a problem. Speed on paper and speed in combat are different creatures. The Merlin Ekan engines, fitted to early production Mosquitoes, were rated for specific boost pressures, 14 pounds per square inch for takeoff, less for sustained cruise. These weren't arbitrary limits. Rolls-Royce engineers had calculated detonation margins, bearing temperatures, piston crown stresses with obsessive precision. Exceed those figures, and catastrophic failure became probable. Shattered connecting rods, melted pistons, engines tearing themselves apart at 20,000 feet over hostile territory. The manuals were explicit. The limits were sacred. Violate them at your peril. Yet by late 1942, as Mosquitoes began flying regular sorties deep into Germany, crews were reporting something troubling. They were fast, yes, but not quite fast enough. The Luftwaffe's Focke-Wulf 190 and the latest Messerschmitt Bf 109G variants were closing the gap. Interceptions were becoming uncomfortably frequent. A Mosquito bounced over the Ruhr, might outrun its pursuer, but the margin was thinning. Pilots returned with stories of tracer rounds, passing closer than they'd like, of dives that barely opened distance, of engines screaming at emergency power that still wasn't quite emergency enough. The Mosquito had proven de Havilland's vision, but now it needed something more, something the design office hadn't anticipated, and the manuals explicitly didn't permit. It needed someone willing to look at engineering tolerances and see not limits, but possibilities. Someone who understood that rules written in peacetime laboratories might not survive contact with war's brutal arithmetic. Someone willing to risk everything, career, reputation, possibly lives, on the belief that the Merlin could give more. It needed Roderick Banks. Banks wasn't supposed to change anything. His job description was clear, his position in the Royal Air Force hierarchy even clearer. He was a fitter, not an engineer. That distinction mattered enormously. In 1942's RAF, engineers designed, fitters executed. Engineers theorized, fitters tightened bolts. The system worked because men like Banks followed manufacturer specifications exactly, religiously, without deviation. Except Banks had a peculiar habit that set him apart from most fitters at RAF Marlin in Norfolk. He read not just the maintenance manuals that told him which bolts to torque and which gaskets to replace. He read everything. The engineering specifications that Rolls-Royce included with engine deliveries, dense technical documents most fitters ignored, filled with thermodynamic calculations, metallurgical tables, stress analyses, detonation chemistry. Banks studied them during meal breaks, tracing the logic behind boost limits and fuel mixture ratios, understanding not just what the rules were, but why they existed. His education had been unconventional, but thorough. He joined Rolls-Royce's Derby factory as an apprentice in 1935, spending 4 years immersed in Merlin development before the RAF recruited him when war broke out. He'd watched these engines evolve from design sketches to production hardware. He understood them at a level unusual for someone wearing sergeant's stripes, understood their strengths, their weaknesses, their hidden margins. What Banks noticed in early 1943 was a discrepancy. The manuals specified maximum boost pressures, 18 PSI for the Merlin Ekan X, but the engineering data, the actual test results, the material specifications, the to component tolerances, showed the hardware could theoretically withstand more, not dramatically more, but enough to matter. The limit wasn't about what the metal could survive under ideal conditions, it was about what Rolls-Royce could guarantee, across thousands of engines, operating in varying conditions, maintained by mechanics of varying skill, fueled with petrol, of varying quality. The published limit was a safety margin, a conservative buffer. Banks began wondering what would happen if you deliberately ate into that margin, just a little. On engines you knew were in perfect condition, maintained by skilled hands, running on verified high-octane fuel. The mathematics were seductive. Power output in the Merlin related directly to manifold pressure, the boost forcing air and fuel into the cylinders. Increase boost by 2 pounds per square inch, and you gained roughly 100 horsepower. On a Mosquito, that translated to perhaps 15 additional miles per hour at altitude. Doesn't sound like much, until you realize that 15 miles per hour is the difference between a successful evasion and a very brief combat career. But the complexity beneath those simple numbers was treacherous. Push too much boost through an engine, and detonation becomes inevitable. Detonation, not to be confused with normal combustion, is when the fuel-air mixture explodes prematurely, before the spark plug fires, hammering the piston with shock waves that can crack cast aluminum in seconds. The Merlin used 100-octane fuel, which resisted detonation far better than the 87-octane fuel available early in the war. But it wasn't infinite protection. High octane bought you margin, not immunity. Banks realized the detonation margin depended on precise fuel mixture control. Run too lean, too much air, not enough fuel, and cylinder temperatures soared, bringing you closer to detonation threshold. Run too rich, excess fuel, and you wasted the power advantage. Fouled spark plugs created carbon deposits. The sweet spot was narrow, and it shifted with altitude, throttle position, atmospheric temperature. He started small. A single Merlin scheduled for overhaul became his laboratory. He adjusted the boost control unit, a seemingly minor recalibration, advancing the overboost cutoff by just 2 PIs. Then he enriched the fuel mixture slightly at high power settings, adding cooling through evaporation. The additional fuel didn't just burn, it evaporated inside the cylinder, absorbing heat that would otherwise stress the aluminum pistons. On the test stand, the engine howled at pressures Rolls-Royce manuals classified as emergency only, maximum duration 5 minutes. Banks ran it for 10 minutes. 15. Temperatures climbed but stayed within acceptable ranges. Nothing shattered, nothing melted. The pistons emerged intact when he stripped the engine down for inspection. No abnormal wear patterns, no incipient cracks. The evidence was compelling, but evidence and permission were entirely different things. RAF engineering officers lived in perpetual terror of unauthorized modifications. Every change, no matter how minor, required approval through channels that moved at bureaucratic speeds, designed to prevent exactly what Banks was proposing. Committees reviewed proposals, risk assessment boards evaluated failure modes, forms were filed in triplicate. The process could take months, sometimes years. Banks's modifications existed in a gray area, not explicitly illegal, because no regulation specifically anticipated anyone would try this, but absolutely unsanctioned. He needed an advocate, someone willing to gamble reputation, possibly career, on a fitter's intuition. He found one in squadron leader Peter Channer. Channer had flown 3 combat tours in Mosquitoes, accumulating a healthy disrespect for official caution, and a keen understanding of survival margins. He'd flown the sortie over Cologne in February 1943, when a Bf 109G had nearly caught him during egress. Close enough to see the German pilot's oxygen mask, close enough to watch tracer rounds arcing past his canopy. The memory made him receptive when Banks explained what he'd discovered. Channer's response was pragmatic to the point of cynicism. If it works, it's not illegal, it's initiative. If it fails, you carry the blame, not me. They chose a Friday evening, when the station engineering officer was away on leave. Banks and 2 trusted riggers worked through the night, modifying the boost controls and fuel system on Channer's assigned Mosquito, serial number DZ414. By dawn, the aircraft sat on the dispersal, externally identical to every other Mosquito on the squadron. Only the maintenance log betrayed the truth, and Banks's entry was deliberately vague. Fuel mixture optimization, routine adjustment. The morning after the modifications, Channer took DZ414 up alone. Standard test flight profile, climbed to 15,000 feet, level flight at cruise power, checked temperatures and pressures. Then the moment of truth. Channer advanced the throttles smoothly past the normal stops, watching the boost gauges climb past 80, settling at 20. The Merlin's note deepened, not the ragged scream of an engine being tortured, but something harder, more purposeful. The airspeed indicator unwound past numbers Channer had never seen in level flight. 395 miles per hour, 405. He grinned despite himself. Cut the throttles back, checked temperatures, everything within limits. He'd just flown faster than a stock Spitfire MiG-5, in a bomber, made of wood. 3 weeks later, he'd prove it could save his life. April 19, 1943. The weather was perfect. Clear skies, unlimited visibility, precisely the worst conditions for a Mosquito trying to stay unnoticed. Channer's mission was straightforward. daylight photographic reconnaissance of synthetic oil plants in the Ruhr Valley. The sort of target that invited attention from every Luftwaffe controller within radar range. The Mosquito crossed the Dutch coast at 24,000 feet. Cameras warming up. Channa's navigator calling out landmarks through the intercom. 18 minutes into enemy airspace, the navigator's voice changed. Contacts, 7 o'clock high, climbing. 2 Focke-Wulf 190 A5 Sevets, vectored from an airfield near Münster. Their BMW radial engines clawed for altitude, the German pilots executing textbook intercept geometry, positioning ahead of the Mosquito's track, cutting off the escape route back to the North Sea. Channa spotted them at 6 miles. 2 dark specks against cumulus, turning to attack. He completed the camera run first. No point in risking his life for blank film, while the FW-190 Sevet ate the distance between them. Then he spoke quietly to his navigator. Let's see what Banks gave us. The throttles were already at maximum for normal operations. Now Channa pushed past the stops, activating the override, advancing into territory. Rolls-Royce manuals marked forbidden. The boost gauges surged to 20 PSI, then fractionally beyond. The Merlins responded with a snarl that vibrated through the airframe. The acceleration wasn't gentle, it was visceral. The Mosquito leapt forward like it had been kicked. Channa felt himself pressed back into his seat as the airspeed indicator swept past 400 miles per hour, still climbing. The altimeter began unwinding, despite full throttle. They were trading height for speed in a shallow dive that maintained energy while opening the gap. The lead FW-190 pilot recognized what was happening and adjusted, pushing his aircraft into a steeper dive to maintain pursuit. For 30 seconds, he held position, perhaps even closed slightly. The Focke-Wulf was fast in a dive, capable of touching 430 miles per hour straight down, but it couldn't sustain that speed. The BMW 801 radial, powerful as it was, had limits. The German pilot was already pushing against them. Channa watched the gap stretch. 500 yards became 600, 700. The Focke-Wulf was at maximum sustainable speed. The Mosquito was still accelerating. At 800 yards, outside effective gun range, the German fighters broke off, their pilots no doubt cursing, fuel states probably critical, the wooden British bomber disappearing into the haze. Channa maintained full power for another 3 minutes, crossing back into friendly airspace over the Scheldt estuary, before finally easing the throttles back. The Merlins settled into cruise, temperatures elevated but within acceptable limits. Both engines had survived. More importantly, so had he. The intelligence officer, who debriefed Channa, noted the encounter clinically in his report. Successfully evaded 2 FW-190 Sevet through speed advantage. What the report didn't capture was the significance. The Luftwaffe's premier interceptor, specifically designed to catch Allied bombers, had been outrun in level flight by an aircraft it should have destroyed. This wasn't luck, it was physics winning. And word of that victory spread through Mosquito squadrons faster than any official communication could travel. By May 1943, 3 more Mosquitoes at Marmon had received Banks's modifications. By June, Banks was spending evenings working on engines from other squadrons, his workshop becoming an unofficial performance center. The modifications remained technically unsanctioned, but they were increasingly tolerated by station commanders who cared more about returning crews than regulatory perfection. Combat reports accumulated through the summer. On June 17, a modified Mosquito outran 3 Messerschmitt Bf 109 G6S over Hamburg. On July 3, another escaped pursuit by Kurt Booligan, an ace with 112 victories, who knew precisely how to prosecute an interception. He couldn't catch the Mosquito. On August 22, a crew limping home on one engine after flak damage used Banks's modifications on the remaining Merlin to stay ahead of 2 Bf 109s that should have finished them easily. The statistics became undeniable. Mosquitoes with modified engines were returning from sorties that conventional aircraft didn't survive. Loss rates for Banks modified machines ran at less than half that of standard Mosquitoes flying comparable missions. Survival bought experience. Experience bought better results. The cycle was virtuous, but Banks couldn't handle the demand alone. He began training others, carefully selected fitters, who demonstrated both technical aptitude and appropriate discretion. He'd invite them to observe an engine modification, explaining theory while his hands performed practice. The boost control adjustment, the fuel jet replacement. Each procedure demonstrated twice, then the student attempted it under supervision. Banks rejected anyone who couldn't articulate why each modification worked, not just how to execute it. Understanding prevented catastrophic mistakes. Flight Sergeant Thomas Yardley became Banks's most accomplished student. Yardley had spent 3 years at Rolls-Royce's Hillington factory near Glasgow before joining the RAF, and he possessed an intuitive grasp of thermodynamics that Banks recognized immediately. By November 1944, Yardley was modifying engines at RAF Coningsby, extending the benefits to Lancaster squadrons, receiving Merlin-powered variants. Corporal James Dennison established another node at RAF Wittering, focusing exclusively on Mosquito squadrons. Dennison's contribution was refining fuel mixture adjustments for different operational profiles. Low-level anti-shipping strikes needed different settings than high-altitude reconnaissance. Dennison worked out the variations, creating mission-specific engine configurations. The unofficial network operated through careful information control. Modifications were never discussed over telephone lines or mentioned in official correspondence. Knowledge passed face-to-face, mechanic to mechanic, usually during station visits that officially concerned routine maintenance matters. Squadron engineering officers developed plausible deniability. They knew something was improving engine performance, but paperwork showed only standard overhauls. If questioned by higher authority, they could honestly claim ignorance of specifics. This arrangement suited everyone except the regulations. Air Ministry directives still required all modifications to receive formal approval, testing, documentation. Banks's network violated that structure entirely, operating as a shadow system optimizing aircraft through channels bureaucracy didn't acknowledge. The situation was sustainable only because results overwhelmed objections. February 18, 1944. Amiens prison in northern France held 120 members of the French resistance, scheduled for execution by the Gestapo the following day. London received desperate messages through SOE networks: break the walls, give them a chance to escape, or they die. The mission required Mosquitoes to strike a 3-story building with 500-pound bombs, breaching specific walls without collapsing the entire structure onto the prisoners. Low-level attack, broad daylight, 300 miles into occupied territory, then the flight home through alerted defenses. Group Captain Percy Pickard took command, assembling crews from 140 Wing. 19 Mosquitoes lifted from RAF Hunsdon on the morning of February 18. The execution date had been moved forward. The formation flew wave-top height across the channel, navigation by stopwatch and compass, arriving over Amiens at precisely 12:03. Pickard's aircraft led the first wave. 6 Mosquitoes climbed to 150 feet for their attack runs. The bombs struck perfectly, sections of outer wall exploding into rubble, breaching the eastern wall near condemned cells. The second wave targeted guard quarters, collapsing buildings, and creating chaos. Intelligence later confirmed 258 prisoners escaped, including most of those scheduled for execution. But the bombing was merely the first problem. The attack occurred at midday, German radar fully alert. As the Mosquitoes regrouped for return, Luftwaffe controllers scrambled every available fighter from airfields between Amiens and the coast. The British aircraft faced 40 minutes of exposure, flying over countryside, where every road held Wehrmacht units with radio communication. Pickard never made it home. 2 FW-190s caught him near Beauvais, guns finding the aircraft before evasion was possible. 2 other Mosquitoes fell to fighters in those brutal minutes after the attack. The remaining 16 aircraft survived largely because of Banks's modifications. Squadron leader Ian McCritchie, leading the second wave, encountered 4 FW-190s climbing to intercept near Abbeville. His modified Merlins gave him the 10 miles per hour that transformed potential combat into a foot race he could win. The German pilots fired optimistically at maximum range, their 20 mm rounds falling away behind McCritchie's tailplane As the gap expanded, Flight Lieutenant Bob Iredale faced more sustained pursuit. A Bf 109 G6 bounced him from clouds south of Amiens, the German pilot executing a textbook attack. Iredale slammed throttles forward, feeling the engine note change as boost pressure climbed into Banks's modified range. For 3 minutes, both aircraft screamed across Picardy. At full power, the 109 holding position, about 600 yards astern, close enough to worry, too far to kill. Then slowly, incrementally, the gap opened, not dramatically. At low altitude, air density robbed both aircraft of performance, but Iredale's Mosquito maintained 405 miles per hour, where the 109 could sustain only 395. 10 miles per hour, compounding across 3 minutes, became half a mile of separation. The German pilot fired a final burst at impossible range and broke away. 12 of the returning Mosquitoes carried Banks's modifications. All 12 made it home. The 4 losses included Pickard's unmodified aircraft and 3 others flying standard specifications. Sample size was small, statistics not definitive, but crews drew their own conclusions. Hermann Göring's rage was becoming legendary. During a meeting at Carenhall on March 8, 1944, he interrupted a Luftwaffe technical briefing to demand why German fighters couldn't catch wooden British furniture. The Reichsmarschall's frustration was understandable. Mosquitoes were appearing over Berlin in daylight, photographing the chancellery, while Bf 109C scrambled uselessly below. The humiliation was tactical, political, and deeply personal. Göring had promised Hitler air superiority. Instead, plywood bombers mocked that promise at 400 miles per hour. The Luftwaffe's response revealed desperation disguised as innovation. Messerschmitt received urgent directives to extract more speed from existing airframes. The solution was the Bf 109 G10, introducing a Daimler-Benz DB 605D engine with improved supercharging and emergency boost, raising output to 2,000 horsepower. On paper, impressive. In practice, the modifications added weight that partially negated the power increase. The G10 could touch 426 miles per hour at optimal altitude, but only briefly, and only if the pilot accepted engine life, measured in hours rather than days. German maintenance logistics couldn't sustain such abuse across operational squadrons. Focke-Wulf pursued the Tau 152. Kurt Tank's obsessive refinement of the FW 190 design. Longer wings, pressurized cockpit, Junkers Jumo, 213 engine producing 2,050 horsepower with MW50 methanol water injection. The prototypes achieved remarkable performance, 472 miles per hour at 41,000 feet, altitude capability that should have dominated Mosquito operations. But development consumed time Germany didn't possess. The first Tau 152S reached operational units in January 1945, too late and too few to affect strategic outcomes. The Luftwaffe also attempted mimicking Banks's approach, unauthorized boost increases on existing engines. Several fighter staffels experimented with adjusting boost controls on DB 605 and BMW 801 power plants, seeking the margin British pilots apparently enjoyed. The results were catastrophic. German engines lacked the Merlin's robust construction and suffered from increasingly poor manufacturing quality as Allied bombing disrupted production. Bearings failed, pistons cracked, connecting rods punched through crankcase walls. A Bf 109 disintegrating over its own airfield because the pilot demanded too much became a cautionary training film. The fundamental problem wasn't merely engineering, it was industrial capacity under siege. Rolls-Royce's Derby and crew factories operated with consistent material quality, skilled labor pools, uninterrupted supply chains. German aero engine production, by 1944, involved dispersed facilities, slave labor of varying skill, materials substituted when proper alloys became unavailable. Tolerances suffered, quality control became theoretical. An engine that measured correctly, on paper, might hide flaws emerging only under stress. Oberst Adolf Galland, General der Jagdflieger, understood this reality with bitter clarity. In an April 1944 memorandum to Göring, Galland noted that even when German fighters achieved successful interceptions of Mosquitoes, the bombers often escaped through sustained high-speed flight that our aircraft cannot match without risking mechanical failure. He requested permission to withdraw fighters from less critical areas, concentrating overwhelming numbers against Mosquito routes, accepting losses elsewhere to guarantee kills against the fast bombers. Göring rejected the proposal, remaining convinced that technical solutions existed, that German engineering superiority would produce aircraft to humble British plywood. The jets did eventually fly. The Me-262 was indeed fast enough. But they arrived in handfuls when hundreds were needed, piloted by hastily trained crews, burning fuel Germany couldn't spare. Banks's modifications carried genuine risks he never downplayed. Engines running elevated boost pressures, accumulated fatigue faster than standard power plants. Components that might normally survive 200 hours between overhauls sometimes required replacement at 150 hours. Piston crown erosion occurred more frequently. Exhaust valves showed increased wear. The performance came with a maintenance bill someone had to pay. More seriously, catastrophic failures did occur. December 1944, a Mosquito taking off from RAF Woodbridge suffered connecting rod failure in the port engine at 400 feet. The rod punched through the crankcase. Oil sprayed across hot exhaust manifold, and fire erupted immediately. The crew nursed the aircraft around the circuit on the remaining engine and landed successfully, but fire destroyed the wing before ground crews could extinguish it. The post-accident investigation revealed the failed engine had been modified 3 weeks earlier. Banks examined the wreckage personally. The failed connecting rod showed fatigue, cracking consistent with excessive loading over multiple flights. Service records indicated 178 hours since overhaul, within normal limits. But Banks had specified modified engines be pulled at 150 hours, regardless of apparent condition. The responsible fitter had missed the deadline by 20. Those hours had cost an engine and nearly killed 2 men. The incident prompted Banks to formalize his informal network slightly. He created a simple tracking system, a notebook where each modified engine received an entry with serial number, modification date, and hour limit. Copies went to trained fitters with explicit instructions: pull the engine at the limit, regardless of how healthy it appeared. The extra conservatism reduced failure rate to near zero over subsequent months, though it increased maintenance workload. Between June 1944 and March 1945, Mosquitoes with modified engines flew approximately 3,400 operational sorties. Combat losses totaled 11 aircraft, a loss rate of 0.32%. Standard specification: Mosquitoes flying comparable missions lost 47 aircraft from 6,800 sorties, 0.69%. The modified aircraft were statistically twice as likely to return. But those same modified engines suffered 23 mechanical failures, severe enough to force emergency landings or abandonments. 3 crews died in crashes directly attributable to engine failure. Another 7 suffered injuries. The moral arithmetic troubled Banks more than he admitted. Each modification he approved might save a crew from German fighters, but simultaneously place them at risk from their own power plants. Ernest Hives didn't announce his visit because he wanted to see reality, not a sanitized version prepared for management inspection. The managing director of Rolls-Royce's Aero Engine Division arrived at RAF Marham on February 12, 1945, driving himself in a borrowed Air Ministry staff car. He found Banks in workshop 3, elbow deep in a Merlin that had accumulated 147 hours since its last modification. Hives watched silently for 10 minutes before speaking. "Show me what you're doing, Sergeant." "All of it." The conversation that followed lasted 3 hours. Banks explained the boost control modifications, demonstrated the fuel jet replacements, walked Hives through his decision matrix for selecting which engines received treatment. He didn't apologize or justify, he simply presented technical reality and combat results. Hives asked precise questions about detonation margins, bearing loads, thermal stresses. This wasn't an interrogation, it was two engineers discussing problems most people couldn't comprehend. Hives had brought service records for 200 Merlin engines randomly selected from operational squadrons. He spread them across a workbench, sorting modified from standard power plants, based on wear patterns visible in documentation. The modified engines showed measurably higher component wear, exactly as Banks predicted. But failure rates remained within acceptable bounds, provided maintenance discipline stayed rigorous. What surprised Hives was consistency. Banks's modifications weren't random tinkering, they represented a coherent engineering approach, applied systematically. Hives asked about failures. Banks provided his notebook, 23 mechanical failures, across 3,400 sorties, a failure rate of 0.68%. Hives compared this to the standard Merlin's operational failure rate of 0.31%. Modified engines failed twice as often, but aircraft equipped with them survived combat at twice the rate. Net effect, fewer dead aircrew. Hives' response surprised everyone present. Rather than ordering the modifications stopped, he thanked Banks for identifying performance margins Rolls-Royce had been too conservative to exploit. The company had indeed built substantial safety factors into the Merlin's ratings. Combat operations revealed those margins were larger than necessary. Banks hadn't discovered anything Rolls-Royce engineers didn't theoretically know. He'd simply been willing to act on it, without committee approval. Within weeks, Rolls-Royce issued Technical Service Bulletin 184, dated March 7, 1945. The document authorized increased boost pressures for Merlin engines in specific applications, essentially codifying Banks's modifications with official sanction. The bulletin specified conditions: engines must be fresh from overhaul, operating on verified 100-octane fuel, with mandatory inspections at 150-hour intervals. Enriched fuel mixture became standard for high-power settings. The bulletin transformed Banks's grey market modifications into approved procedure overnight. What had been technically illegal became officially sanctioned, retroactively, justifying 2 years of unauthorized engineering. Recognition arrived in peculiar forms. Banks received promotion to warrant officer in April 1945, unusual for someone without aircrew qualification. The citation mentioned exceptional technical contributions to operational effectiveness, bureaucratic language, concealing actual achievement. Several pilots, whose lives had been saved by modified engines, wrote personal letters, though most simply shook his hand during station visits, and said nothing more. The best thank you was coming home alive. Rolls-Royce offered Banks a position at Derby, after war's end, a role in experimental engine development, where his willingness to push boundaries would be asset rather than liability. He accepted, leaving the RAF in September 1945, with a service record describing him as competent and reliable, damning with faint praise that entirely missed the point. The final operational tally recorded June 1945, Mosquitoes equipped with modified engines flew 8,200 sorties in the war's final year, losing 27 aircraft to all causes, 0.33%. Standard Mosquitoes in the same period, 4,100 sorties, 31 losses, 0.76%. Statistical evidence was overwhelming. Banks's modifications cut combat losses by more than half, saving roughly 200 aircrew lives through simple mechanical adjustments that cost nothing but careful attention. Roderick Banks died in 1992, age 76, in suburban Derby, where he'd spent 47 years refining engines for Rolls-Royce. His obituary, in the Derby Telegraph, mentioned a distinguished career in aerospace engineering, but said nothing about Mosquitoes or wartime modifications. The story might have disappeared entirely, except for a chance conversation at a 1995 Mosquito reunion, where 3 veterans independently mentioned Banks's engines, and a historian finally asked what that meant. What became clear was that Banks achieved something rare, meaningful tactical innovation from below. A sergeant identifying performance margins that engineers and officers had missed or feared to exploit. His success revealed uncomfortable truths about engineering conservatism. Rolls-Royce's safety margins, whilst prudent for general application, were excessive for engines maintained to higher standards and operated by skilled crews. Banks recognized that safe for all conditions wasn't the same as optimal for specific conditions. The modifications also illustrated the difference between engineering in peacetime and war. Peacetime prioritizes longevity, cost-effectiveness, safety margins, accommodating imperfect maintenance. War prioritizes survival, accepting reduced component life if it keeps crews alive today, regardless of tomorrow's maintenance bills. Banks understood that an engine surviving 150 hours instead of 200 was acceptable if those 150 hours prevented a crew dying in minute 47. Modern military aviation still grapples with this tension. Fourth and fifth generation fighters have official performance limits and unofficial combat limits pilots use when survival demands it. The F-15's engine, for example, has standard thrust ratings and emergency ratings that shorten engine life but provide crucial performance. Banks pioneered this doctrine for his era. The Mosquito's post-war reputation benefited enormously from modifications it carried during conflict. Performance figures cited in histories often reflected Banks' modified aircraft, not standard specifications. The Mosquito became legendary, partly because Banks made it faster than de Havilland's original design. Engineering education occasionally examines Banks's work as case study in practical problem solving versus institutional procedure. Banks's workshop at Mons was demolished in 1962 during station modernization. Nothing marks the location where he modified DZ-414 or trained fitters who spread his techniques across squadrons. The Mosquito that carried his modifications to Operation Jericho survived the war and was scrapped in 1947. Its historically significant engines melted down for aluminum value. Yet Banks's influence persists. Modern engine development incorporates field feedback mechanisms specifically designed to capture the kind of insights he generated. Rolls-Royce's successor companies maintain formal channels for field service representatives to report unusual but successful operational practices, institutionalizing what Banks did informally. The Mosquito's legend endures because it succeeded spectacularly at missions everyone said were impossible. It flew to bombed Gestapo headquarters with precision. It outran the Luftwaffe's best fighters through 6 years of war. That success rested on Geoffrey de Havilland's brilliant design, certainly, but also on a mechanic who read the manuals, understood the margins, and decided that saving lives justified bending rules no one even knew could be bent.